Hi Year 13. I'm going to use this video to go through some more examples of forming differential equations. If I do some of the odd numbered questions on the exercise, I think it might be appropriate to leave you to do the even ones. I'm going to do 1, 3, 5 and 7 and then leave you to do 2, 4, 6, 8 and I believe there's a number 9 as well that you might want to do as well. So hopefully you've already watched my long video on forming differential equations and you've seen a couple of examples already. So I'm going to use some of the acquired knowledge that we've got in that video to deal with some of these questions. So question 1, you've got the rate of increase of a population of rabbits. We've seen this before, haven't we? Is given by this equation here. dp by dt is kp. K is a positive constant. We've also got initial conditions here. Initially, the population is of size 200. And we're solving in terms of giving p in terms of k and t. Okay, I'm going to go straight into that. So solving my equation. I have done this before in the previous video, but you can skip this if you know what's going to happen. So I'm going to divide, integrate both sides. So then I get natural log of p is kt plus c. And then p is the exponential of kt plus c. Break the constant apart and you get p equals a e to the kt. Using our initial conditions, initially we've got size 2200 for our population. So when t equals 0, p equals 200. Put that into here. So that means that 200 equals a e to the power of 0 because k times 0 is 0. And then that just leaves me with a. So if 200 equals a, I can rewrite this. So p equals 200 times e to the kt. And that's part A done. Part B, we're moving on with this now. So given that k equals 3, we can find the time taken to reach 4,000. So if my population is meant to be 4,000, then I can replace k with 3. This is 200 e to the 3t. So now I need to solve that for t, which is time. So I'm going to divide by 200. That's going to give me 20. That's e to the 3t. Now I'm going to take natural logs. Natural log of 20 is 3t, and then divide by 3. Equals t. Okay, so t is given in years. I'm going to do this as a rough decimal by typing it into my calculator. That's 0.999 years. And that's given to 3 significant figures. Okay, so basically a year then. State a limitation of this model for large values of t. This is quite a common end to a question in that it's asking you to consider what happens when t gets very large. So what's either going to happen is that your population is going to get very big and go off to infinity. And that's going to happen if it's e to a positive power. That's going to happen. But if this power is negative, then your population is going to die off towards 0. So this will happen, it will go towards 0 when you've got e to a negative power. Okay, so it's worth distinguishing between those two cases. Okay, e to the power of something positive gets very big, and e to the power of something negative gets very small. So in this case, we've got e to the 3t. So as this is for part C, as t goes to infinity, we're going to have p goes to infinity because it's e to the power of something positive, which isn't feasible, is it? Because we've got some population of rabbits that clearly isn't going to go to infinity because there's going to be some kind of limiting factors there. Okay, so maybe I'll put this as well. Other factors. There might be some predators about. There might be something else in the environment that's stopping this population from growing too high. Okay, that's question 1. That's worth 8 marks total, and that's the kind of thing that you're expected to write down. Okay, moving on to question 3. This is the thickness of ice, which is x in centimeters on a pond. increasing at a rate inversely proportional to the square of the existing thickness of ice. Okay, so quite a complicated sentence, but we'll break it down. So x is the thickness. We've got an increasing rate. So this is going to give us our dx by dt, because rate is derivative with respect to time. We've got inverse proportion, which means we're going to get k divided by something for our expression, but it's the square of the existing thickness of ice. Okay, so this part is going to give me k over the square of x. Okay, so that improves upon what we've written in blue. And then we've got some initial conditions here. Initially we've got thickness is 1, and after 20 days the thickness is 2. So we're going to solve some equation, get to here. So we'll start by setting up our proportionality statement. We've got dx by dt. This is for part A, is inversely proportional. So it's k over x squared. And that's set up. Now I can solve this. I'm going to put things on their appropriate side. So x squared dx equals k dt, which I'm going to integrate on both sides. X cubed over 3 equals kt plus c. Okay, it might be a good idea now, once you've got rid of your differentials, and you're back to just x in terms of t and constants, it might be a good idea to now use your initial conditions. So initially we've got a thickness of 1, so when t equals 0, x equals 1, so that means that 1/3 equals 0 plus c, which means that c is a third obviously, and then after 20 days we've got a thickness of 2. So let's rewrite again. So you've got x cubed over 3 equals kt plus a third. Okay, probably makes sense to times by 3 now because of this third here and third here. So x cubed equals 3kt plus 1. So now you've got when x is 2 when t is 20. So now we can put that in. So we've got 8, which is 2 cubed, is 3k times t, which is 20, plus 1. This makes it into 60k. And then solve for k, so k is going to be 7 over 60. Okay, brilliant. So now I can go back to my equation here. I can rewrite x in terms of t. So x cubed equals 3 lots of k times t plus 1. The 3 and the over 60 will make my over 20, and then I can take the cube root. And that's exactly what I was supposed to show, so we're done. Now all of that's worth 7 marks, and it's up to you where you want to use your initial conditions, but it helps to do it in a sensible place where it's easy to sub in and then easy to rearrange. So that's part A done. The time taken to increase the ice from 2 to 3. Well, I'm going to need 2 separate times here because I'm going to need the time that it takes to get to 2 centimeters, which we know is 20 days. And then I need the time to get to 3 centimeters, and then I need some kind of difference. So let's make our x equal 3. This is for part B. So the cube root of 7/20 of t plus 1. I'm now going to solve for t, so I'm going to cube. So that means that 27 equals 7/20 t plus 1. We're then going to solve for t. So that means that 26, and then I'm going to times by 20 and then divide by 7 equals t. Okay, so what's that? I'm going to type that in as a fraction. 20 times 26 divided by 7 is 520 over 7. The difference then is the difference between this time and 20. And that leaves me with 380 over 7 days. And that's, as a decimal, roughly 54.3 days. Okay, excellent. You can check the mark scheme with this. If I've made any mistakes, then you can figure out what I've done wrong maybe, and then check with the mark scheme. Okay, next one, we've got number 5. The rate of change of the surface area of a drop of oil, a millimetres squared at time t minutes, can be modelled by this equation. So this time it's given you the equation straight away. You don't need to form it this time. Given that the surface area of the drop is 1 millimetre squared at t equals 1, find an expression for a in terms of t. Okay, so this is straightforward. Solve the equation, plug in your initial conditions and see what you get for the constants. So let's start off by writing our equation again. Let's get the a onto the dA side, but that's going to give the power negative. And then I'm going to get 1 over 10t squared dt. Okay, it will probably help to write this as a power of t because the t is on the bottom. So I'm going to do that first of all. Okay, I'm going to not integrate one side without integrating the other because that's going to cause me some problems. So this is 1/10 t to the minus 2 dt. Now I'm good to go. So integrate the a's. I'm going to get a to the minus a half divided by minus a half. And then on this side I'm going to get a 10th t to the minus 1 divided by minus 1 makes that negative, and then plus c. Okay, let's tidy up. So this gives me minus 2 in front, and then a to the minus half is dividing by the square root of a. That's using some index laws there, and that equals minus 1 over 10t plus c. Excellent. Okay, now I think it might make sense to plug in your initial conditions because that gets rid of this constant. So what have we got? When t is 1, the surface area is 1. So t equals 1, a equals 1. Let's put that in. So minus 2 over 1 equals, that's going to be 1, so it's minus a 10th, plus c. So c equals minus 2 plus a 10th, which is going to be minus 19 tenths, I believe. Yeah, that makes sense. Okay, good. So now I'm going to write this again. Minus 19 tenths. We should probably get rid of the minus signs now because they're all negative. That's going to be plus. Now let's combine these fractions so that I can then flip both sides over and take reciprocals of both sides. So now 2 over root a equals, now the common denominator is going to be 10t. So this first one is going to stay the same, but the second fraction is going to need to times by t on the top and bottom. So it's this. Now I can take reciprocals. So root a over 2 equals 10t over 1 plus 19t. And now I'm going to double both sides. That's going to double the top of the right-hand side. And then I'm obviously going to square to get rid of the square root. Okay, and that's part A done. That's a lot of work there for 7 marks, and hopefully you can get something like that yourself. Now we're going to show that the surface area of the drop cannot exceed this value here. Okay, so this is kind of another limit question. So we're trying to show that this value of A can't be bigger than this value. So let's think about what this fraction in here can be as a value. So let's think about this thing here. So let's think about what this can be. 20t over 1 plus 19t. Okay, so I'm trying to link that with that value here. So Well, it's going to be to do with this denominator here. So this is going to be, if I make the denominator smaller, then this is going to be bigger. Right, so this is less than 20t over 19t squared. There we go. So if I take that 1 off of the denominator, then the entire thing is going to get bigger because the denominator's got smaller. So this thing here is less than this, but then the t's are going to cancel out because that's 20 over 19 squared, which is 400 over 361. Okay, so we're done because a is this, which is less than this, which is this fraction here that we've got. Okay, I guess another way that you could show this is to take this fraction as well, and if I divide everything by t, then this is an alternate way of doing it. You can do 20 over 1 over t plus 19. Okay, that's dividing top and bottom by t. But then you'll notice that this is just going to go to 0 when t goes to infinity. So you're going to be left with 20 over 19 as well. So you can show it that way as well. Okay, right, I think I'm going to stop there with those examples. If you need any more done, then let me know and I can give you some more help. Otherwise, best of luck with your practice. Thanks, Year 13. See you soon.